We present masked scene modeling, narrowing the gap between supervised and self-supervised learning in 3D scene understanding. If you work in 3D scene understanding, you've likely started a new project only to realize there isn't enough data to train a general model for your specific task. Ideally, you'd want a model that can generate general-purpose features for each point in your point cloud. But what should such a model look like? The default solution nowadays is to take advantage of image-based models. First, we process a set of images of the scene to generate per-pixel features, and then these 2D features are aggregated into 3D. This solution has many advantages. Models have been trained on large datasets and therefore have limited domain generalization problems. Unfortunately, these features are not computed into 3D. Working in 2D can generate multi-view inconsistent features due to occlusions or accidental views. So what is the alternative? Can we use a 3D model that generates general features? There are some existing works that have tried to address this problem, but they have several limitations. First, those models are only used as a weight initialization step before fine-tuning the whole model. So the representations learned are not properly evaluated. Moreover, 3D self-supervised models based on a masking and reconstruction objective only reconstruct input features, such as colors. If we look at mask-based self-supervised methods for images, those hide some parts of the image, and the model has to infer those from the remaining ones. But in point clouds, if we mask the colors as existing works do, we can still easily infer those from the geometry, simplifying the reconstruction objective. To address these limitations, we propose masked scene modeling, a framework that receives as input a scene represented as a point cloud. Then, it creates two differently augmented views of the data and voxelizes the scene. These views are further cropped and masked. We input the cropped views through an encoder to generate per-voxel features. Then, we include the masked voxels with a learnable token. Note that here, the encoder has never seen the geometry of the masked voxels, contrary to other works. The decoder then predicts the features of the masked voxels. We supervise our model with a teacher model that processes the full views without crop or mask. As our teacher model, we use the same architecture as the student model, updated with exponential moving average instead of gradient descent, as is commonly done in 2D self-supervised models. The key idea of our approach is that we use this framework in a hierarchical manner with a U-Net architecture. The encoder processes each level in the hierarchy without the mask token. The last level of the encoder passes the features to the decoder, which has to predict the features of the masked tokens. However, the decoder does not have any information about the high-resolution details inside the masked tokens. Something that will happen if we include the mask tokens in the encoder as existing methods do. Then, the decoder process to do the same with the next level of the hierarchy in a bottom-up reconstruction manner. Once our model is trained, it is able to produce general features. Here you can see some visualizations of the features after applying PCA to reduce the high-dimensional features to 3 and visualize them as color. Similar objects result in similar features, as the chairs in the left image and the couches and plants in the right image. We also evaluated our model quantitatively on the task of semantic segmentation. We freeze the model and produce features that are used in a nearest neighbor setup, where we classify points by searching the most similar ones in the training data, and in a linear probing setup, where we only train a linear layer to predict the point class. Results show that our method outperforms state-of-the-art methods and produces similar results to the same model trained from scratch. Moreover, we also evaluated the model on other 3D scene understanding tasks, such as 3D visual grounding. Here, the model, given a 3D scene and a text description, has to find the object that matches the text. Results on this experiment indicate that our model again outperforms state-of-the-art methods and has similar performance to the same network trained from scratch. Moreover, our model also outperforms features from different 2D models aggregated in a multi-view manner. In conclusion, in this work, we have introduced the first self-supervised model that is able to generate general features that can be used off the shelf without fine-tuning. Does not suffer from the same limitations as existing works. and is able to achieve similar or even better performance than models trained from scratch.